So, welcome to this problem sessions of the course Introduction to Abstract and Linear Algebra. So, my name is Harshita. I'm a PhD student of ISO Tirupati. Today, we'll be looking at the contents of week 4. Some problems related to the content of week 4. I hope the screen and audio is okay. If not, you can just type in the chat box if there's any issue at any point of time. And in the process, we will, revise some concepts which are needed to solve the question. So we have a group, G is GL2R, and H is some subset of this group G, right? So first of all, can one of you tell me what is the operation in this group? So we have G. I hope you know what is GL2R. It is all invertible matrices with entries in R. Either you can look at it, you can look at it as all the matrices M2R, which means all those matrices such that A is invertible, or equivalent way of saying it is determinant of A is not equal to 0. So can one of you tell me what is the group operation here? Any answers? You can type in the chat box. Okay, so if nobody wants to answer, let's see. See, you have this M2R itself, right? So you have all matrices. So let's look at this. Let's call it, say, G prime is M2R. Now, this itself is a group. So given any two matrices, so 2 cross 2 matrices, A, B, C, D, what can we do? We can add them. A prime, B prime, C prime, D prime. So you get A plus A prime, B plus B prime, C plus D prime, D plus D prime. Right? So under this operation forms a group. So this you can check. So as a set, this GL2R is actually a subset of M2R, right? It is all those matrices whose determinant is non-zero. So it is definitely a subset of M2R. So this I'll just leave it. So G is a subset of G prime, right? But is it a group under the same operation? When we say something is a subgroup, what do we mean? We mean that whatever is the operation here, under the same operation, does the subset form a group, right? So let us look at that first. So we have invertible matrices. So the question is basically reduced to, is the sum of two invertible matrices invertible? So we are checking the first property. Is the sum of two invertible matrices invertible? Just remember, so just to recall, a matrix, let's say X is invertible if and only if determinant of x is not equal to 0. So it's the same asking, is the sum of two matrices whose determinant is non-zero, is their sum also determinant non-zero? Yeah? Any answers? Is this true? Or do you have counter example? I'm just asking the question, answer to the question. Is the sum of two invertible matrices invertible?
No.
Yeah. So it's right. It's not true because let's just take so
1 0 0 1.
You want to take one matrix as 1 0 0 1, okay?
And 1 0 0 minus 1.
Yeah. So 1 0 0 minus 1. So if you look at this, the determinant of this is non-zero, this is invertible, but when you take the sum, we get 2 0 0 0. This is not an invertible matrix. So the closure property itself is not satisfied. So this GL2, although it is sitting as a subset of M2R, it is not a subgroup. As in, when we say subgroup, I again repeat that when we say something is a subgroup, it's not just a subset, but under the same operation, it forms a group. So it's not a subgroup of M2R. G is not a subgroup of G prime plus. But GL2 itself, you can make it into a group by slightly changing the operation. So instead of addition, we look at multiplication. And this is again a fact that we're using, that if A and B are two matrices, then determinant of the is equal to product of the determinants. So now if you look at it, you look at the set GL2 that we took. So it is all matrices whose determinant is non-zero, right? Now if you take any two matrices in this set, you take A and B. So let A comma B belong to GL2R. So what does that mean? Determinant of A is not equal to 0 and determinant of B is also not equal to 0. So determinant of AB, which is determinant of A, into determinant of B cannot be equal to 0, right? So in fact, GL2, at least the first condition of the group is satisfied, that it is closed under multiplication of matrices. So that is GL2R is closed under multiplication. Okay, so the other properties of the group, whether GL2 forms a group under this matrix, you can verify that it is in fact true. So you can check that. We'll go back to our original question. So the group under multiplication. So that means you have to check the other properties. Maybe I'll quickly orally say it. The associativity, if matrix multiplication is associative, Identity is the identity matrix, diagonal entries 1 and everything 0. Inverse, if a matrix determinant is not equal to 0, it means the inverse exists. So 1 by determinant, the school calculations that we used to do, 1 by determinant A into adjoint matrix, that will give you the inverse of a matrix. Okay, so let's go back to this original question that we were looking at. So basically, when we say G equal to GL to R, it is understood that it is a group under multiplication, because under addition, it doesn't even form a group. Right? So that was the point I was trying to make. Now we have a subset given by all those matrices whose determinant is of a certain form. That means determinant is of the form 3 power some integer. So H is set of all A in G such that determinant of A equal to 3 power k. K is an integer. So the question is this a subgroup? Is this a normal subgroup? Is this a cyclic subgroup, abelian, and so on? Okay. So before checking the other conditions, abelian and everything, let us just see if it is a subgroup itself. Yeah. So how do you check that something is a subgroup? If you remember what we did last time. Anybody wants to attempt?
Ax plus by is equal to 0.
Sorry?
Which is a sub.
Ax plus
X plus by is equal to 0.
what is your
X plus by
Ax by? So what is your Ax, B and y here?
is an this element in H.
Okay.
A and B are element in H.
Okay. So this is not the condition of the subgroup. So if you want to check
A, if A and B two matrices in H, then AB inverse belongs to H.
yeah, that's right. So if you want to check, so how do you check? H is a subgroup of G. So as he said, you take any two random matrices in H. So take A comma B in H, and if AB inverse belongs to H. So when we say take AB in H, we are saying that for every AB in H, that's a more precise way of saying it, for every AB in H, if AB inverse belongs to H, then H is a subgroup. Again, I insist, when we say AB inverse, this inverse and this, this multiplication is with respect to the operations in the group G, the original operations in the group G. Is this clear? Any questions on just this condition? Okay. If not, let's go ahead. So how do you check that AB inverse is in H? Basically, you look at what is the condition that defines H. H is all those matrices whose determinant is of some form, right? So you know that A and B belong to H, which means the determinant of A and B is of this form, 3 power some integer. So you want to check if the determinant of AB inverse is also of the form 3 power some integer. So let's do that. So since A and B belong to H, that means just by the fact that some element belongs to H, it means its determinant is 3 power k. So there exist two integers k1 and k2 such that determinant of A equal to 3 power k1 and determinant of B equal to 3 power k2, right? So here we'll just use one more fact. So if determinant, what is the determinant of A inverse?
3 power k1.
A inverse, or in general for any matrix. Okay, if you want to look at the same matrix, what is the determinant of B inverse? We know
3 power
determinant, yeah, 3 power,
k2.
that is determinant of B. Determinant of B inverse would be, okay, let's look at this. So we can actually prove it using the fact that we've already seen. What is B times B inverse? It is the identity matrix just by definition, right? So if you look at the previous, fact that we saw, if you have two matrices, the product of determinant of the product of matrices becomes the product of determinants. So what do we get? Determinant of B times B inverse equal to determinant of identity matrix. So I is the identity matrix.
So B inverse, determinant of B inverse is 1 by 3 to the power k2.
Exactly. So let me just finish this. That's perfectly right. So you have determinant of B into determinant of B inverse is determinant of identity is 1. Determinant of this is 1. So determinant of B inverse, we are assuming determinant of B is non-zero. I mean, it's 3 power k2, so it's non-zero. It is 1 by determinant of B. So this is true for any matrix. I mean, there's nothing special about B except the fact that it is invertible. The determinant is non-zero. So using this, what we get determinant of B inverse is 1 by 3 power k2, or it's the same as 3 power minus k2. Okay, now let's go back. What were we trying to do? We want to see if this element AB inverse belongs to H. That is our aim, right? So again, looking at the condition of H, it is all those matrices whose determinant is of certain form. So our aim is to compute determinant of A, B inverse. Again, this splits as determinant of A into determinant of B inverse. We have both these values. So this becomes 3 power k1 minus k2. K1 and k2 are integers, so k1 minus k2 is also an integer. So determinant of AB inverse is also of the form 3 power some integer. So we get AB inverse belongs to H. H is a subgroup of G. So any questions?
No, ma'am, we can continue.
Okay. Yeah. So is it abelian? Anybody wants to try this?
It may not possible, may not
So,
be true, I think.
yeah. So can you give a counter example? Can you give two matrices in H which do not commute?
0, 1, 0, 1,
0, 1,
0, 1,
sorry, 0, first row is 0, 1, second row,
it's also 0, 1.
is that an invertible matrix? What is the determinant of this?
Oh, sorry.
Determinant between
Yeah.
0.
Maybe 0, 3. Sorry.
See, once you put a 0 here and a 0 here, then
Yeah, yes.
determinant. So just slightly modify it.
Okay. 1, 0, 0, 3.
1, 0, 0, 3. Okay. So let's A equal to 1, 0, 0, 3. So determinant of A is 3. So it belongs to H. Another example.
3, 2, minus 2, 3.
3, 2, minus 2, 3. Is this in H? 9 minus 9. No, right? What is the determinant of D?
13.
Yeah. So this doesn't belong to H, no?
3, 0, minus 2, 3.
3, I want to make this 0. Yeah. So the determinant of B is 9, which is 3 square. So basically, sorry, I shouldn't have written determinant belongs to A. So A and B belong to H. So let's see what is AB. So can some of you compute BA? So this is I hope my computations are right.
BA is 3, 0, minus 2, 9.
Okay, so this is not minus 2, right? Yeah. So you see that this is not equal to each other, right?
Yes.
So H is
Not a billion.
not a billion. Is it normal? Do you remember what is normal? So let me just recall. A subgroup H dot. So first of all, it has to be a subgroup. A subgroup H dot is normal in G dot if for every G in G, EH equal to HG. I hope you remember these notations. So GH is, you take this element G.
Left coset is equal to right coset.
Yes. So they're called left cosets and right coset. So it is basically this element G multiplied with every element of H. And HG is HG such that HG, right? So what it says is every right coset is also a left coset, and in fact by the same element. So let's go back to our question. So one way is, see, how do you check if something is normal? If H is a normal subgroup of, so see, what does it mean by HG equal to GH? So if I bring this G on the other side, what it becomes as GH G inverse equal to H, right? Just taking this G here, multiplying both sides by G inverse, whatever you see it. Is there something? Okay, there's an answer which says no. We'll come to it. So, what does this mean? You take any element G in the bigger group and you multiply it with some element of H, you get back an element of H. So, that is, so what you can do is take a random element in G and an element in H and just check if G inverse belongs to H, right? This is kind of like a test to see if the subgroup is normal. So, so the answer no was for, okay, it was for something else. Okay, so is H a normal subgroup? Anyone wants to try? It's okay if you don't get the complete answer. Okay, if you just want to try also, you can unmute and see. Okay, so let's just go through the procedure. So we'll take some matrix A in G and some matrix in H. All I'm doing is this step. This is what is being done here. Okay. So we took a matrix A and we took a matrix B. And what do we want to check? We want to check if A inverse belongs to, so want to check, does AB A inverse belong to H? And again, what is the defining property of H? It's all those matrices whose determinant is 3 power an integer. So what is determinant of, so you already know B is in H. So determinant of B is of the form 3 power k for some integer k. So what is determinant of AB A inverse? So the same thing, you can split it up as product of determinants. B into determinant of A inverse. Now you go back and see what did we do about determinant of A inverse. It is nothing but 1 by determinant of A, right? So this is, as I said, this fact is true for any invertible matrix. So this determinant of A inverse, I'll just replace it by 1 by determinant of A. So these two quantities cancel. So we get that it is equal to determinant of B. So, which you already know it is of the form 3 power k. Right? So AB A inverse belongs to H, which implies H is a normal subgroup. So yeah, technically you should write what is the operation also. Is this fine? Any questions so far?
No, ma'am.
Okay. So there was one more option which said, is it a cyclic subgroup? So we know it's not an abelian, we know it's normal. Although we've got the answer, let's just talk about cyclic nature. So one thing is, so it is a slightly, it's a counting argument that you can give and see easily. So let's just see. So if a group is cyclic, what does it mean? One element generates the whole group, right? So a group is said to be a group G is said to be cyclic if there exists some element in G such that every element in G is basically generated by this. When we say generated, it is some power of this G itself. So, I mean, an easy way to see that this is not cyclic is, see, if a group is cyclic, what happens? You're getting it from one element. So you have something like G power 0, which will be identity, G square, G cube, and so on. And you have G inverse, G power minus 2, and so on, right? So this will actually be a countable set, or it can be finite. So when I say countable, we are also considering finite sets, denumerable sets. So any cyclic group will be at most countable group, right? But if you look at our subgroup H, so a cyclic group is either finite or countable. But if you look at our group H, we can show that it is actually uncountable. So one way of looking at it is, so you look at this set of matrices. Real number. So you just take any real number and you look at this matrix where the diagonal entries are A and 0, 3 by A, and the other entries are 0. So what is the determinant of this matrix? 3, right? So in fact, this is contained in H, and this itself is an uncountable set. Because for every real number, we're getting a different matrix. So H cannot be cyclic. So that takes care of all the options. So in fact, even this is not true. Are there any questions? Any comments, or do you have a different way of saying it? Okay, if not, let's go ahead.
Ma'am, a previous slide.
Sorry, this one? You have a question in this previous slide? You can unmute and ask if you have a question. Okay. So the next one, it has two statements and says ask which of them is correct. So the first one, you're given natural numbers under addition and multiplication, and you have integers under with two operations, addition and multiplication. So is it a ring? Is it a commutative ring? Right? So if you just recall what is a ring, so you have some set with two binary operations. Is a ring if under the first binary operation, it forms an abelian group, and under the second binary operation, it forms a semi-group. So this just means the operation is associative. It's a binary operation, you have closure and associative. and you have some kind of compatibility between these two operations. So what does that mean? So you take G dot G1 dot G2 plus G3. This will be G1 dot G2 plus G1 dot G3, and the other way also. So G2 plus G3 dot G1, that also distributes. That's what we call as the distributive law. So this is for all elements. So is the first one a ring?
No, it is not a group, so that's why.
Yeah. So it is not even a group under addition, because if you take, let's say 2, it doesn't have an inverse under addition, right? So statement 1 is false because n plus is not a, forget abelian, it's not even a group. And it's not a group. You take any non-zero element, say 1 does not have an inverse. So inverse of 1 is -1 under the operation of addition. So right? So it is not a ring. And the second statement, is it true?
Yes.
Yeah. So once again, just before you answer, with unity means it has a multiplicative identity. So can you just quickly explain why you said yes? I'm sorry, I don't know who said yes.
It doesn't have a multiplicative inverse.
We don't need multiplicative inverse. So you look at the second condition of a ring, it just says that G dot is a semi-group, which means it's a binary operation which satisfies two properties, closure and associativity. So you don't need a multiplicative inverse for it to be a ring. Okay. So integers under addition, we've already seen that it is a group and it is an abelian group because whether you do 2 plus 3 or 3 plus 2, it's the same. It is commutative. So this is an abelian group. Right? And under multiplication, the operation is closed, right? So product of any two integers is an integer. So and it is also associative. Multiplication is associative. And distributivity also holds. So if you have any two integer, if you have integers like this, you know that this is AB plus AC. So in fact, it is a
Ring.
yeah. But they not just ask for ring, they ask for commutative ring with unity. So commutative means anyway under addition we are demanding that it has to be abelian. So addition it commutes. So when we say commutative ring, it means under this multiplication the operation is commutative, which means AB equal to BE.
Yeah.
which is again true in integers. So it is commutative. And finally, with unity means it has multiplicative identity, which means it has some element such that you multiply any element with, so you have 1 in integers. And if you multiply any element in integers with 1, you get back a, right? So this is multiplicative identity. So in fact, it is a commutative ring with unity. Is a commutative ring with unity. Okay. So we'll move on to the next question. So here they give you a list of rings and ask which of these is an integral domain. So if the operation is not given, so these are standard rings. So we are supposed to know what are the operations. So if you look at Z7 or Z5, what is it? So in class, I think it was denoted like this. And the operation is addition modulo 7 and multiplication modulo 7, which means if you take two elements, let's say plus 6. So what is this? What do? You add the numbers inside. 2 plus 6 is 8. And then you look at the remainder that number leaves when you divide with 7. So 8 leaves a remainder 1 when you divide it by 7. So this becomes 1. I hope this is clear. It was discussed in class also. Oh, I'm sorry. Only page 7.
Ma'am, there is slight lag on the screen. So what you write, it appears after 1 second.
Oh, is it so? Should I speak slower? Okay, can you see what is written now?
Yes, ma'am, now I can see.
Okay, maybe I'll speak a little slower. Or maybe. Okay, is this okay? So how do you add two elements in Z7? You take the whatever is inside the integers 2 plus 6 and you look at the remainder. And the same thing for multiplication. Suppose you want to do 2 into 6. So you do 2 into 6, which is 12. And then you look at what remainder it leaves when you divide it with 7.
5.
Yeah. So
5.
yes, 5. So under these operations, Z7 plus dot, it forms a ring. So we'll not check the part that it forms a ring. And similarly, Z5 plus dot forms a ring. And the last one is matrices. So you have matrices with integer entries. Again, the operation here is multiplication and usual addition and multiplication of addition of matrices and multiplication of matrices. So we can check that this also forms a ring. So here the multiplication does not have inverse, but as we saw, a ring, we don't demand that we have an inverse for every element under multiplication. Okay, so now what is an integral domain? So a ring is said to be an integral domain.
It should be commutative ring with unity.
Yeah, and any more
And should
conditions?
not have and should not have zero divisor.
Yes, exactly. So maybe I'll put commutative ring with unity here. A commutative ring with unity is said to be an integral domain if it does not have any zero divisors. Okay. So just to recall, what is a zero divisor? So an element A is said to be, so first of all, a non-zero element, we are excluding zero. Element A is a zero divisor if there exists another non-zero element such that the product is zero, right? So in other words, if you want to say that it doesn't have zero divisors, what do? You take two elements whose product is zero and you say at least one of them has to be zero. So, I mean, this is just to keep in mind a useful way of looking at it. Nothing new is being said here. So, if we want to say has no zero divisors, we can take A, B in R arbitrary elements which are not zero. Okay. You take any two arbitrary elements and you say that if A be equal to 0, then either A is 0 or B is 0. So in school, when we solved all these equations and we got, something into something is 0, like x minus 3 into x minus 2 equal to 0, we always used to take that either x minus 3 is 0 or x minus 2 equal to 0, right? So what we were doing all the while is saying that real numbers does not have zero divisors. Okay, so with this, let's go back to the question. So which of these is not an integral domain?
Set of all square matrices of order n.
Set of all square matrices of order
N.
n. Okay, so can you give a example? So he's saying that MNZ is not a zero, is not an integral domain.
0 1 0 0 0 0 1 0
0 1 0 0
0 0 1 0.
0 1 0. Okay, so these two are elements of MNZ and A is not equal to 0.
Can we change the second matrix?
Hmm.
Last row is 0 1.
So you're taking the entire zero matrix.
No, second row is 0 1.
Okay. This okay. What is AB? I mean, you look at the last entry, it will be this row into this column, right? Which won't be zero.
Yes.
Can you slightly change your example?
Yes. We have to change it.
So can you change it? See, if you put one here or here, you will face the same problem. So where else can you put your one?
Maybe 1 0.
Hmm?
Second row is 1 0.
Oh, second row is 1, 0.
Yeah.
Even then, when you do this row with this column, yeah, can you slightly change it, or does somebody want to help him? It's almost right. Just
Ma'am, 1000 B.
1000.
yes. So
Second
instead of
matrix 1000. Yes.
yes, instead of see, if you put it in the second row, you will have a problem because of this one. So just put it in the first row. Now you look at AB, it is the 0 matrix. So A is a 0 divisor. In fact, B is also a 0 divisor. Right. Which means M and Z is not an integral domain. That's right. But let's go back and see what happens to Z5 and Z7. So it's true that this is not an integral domain, but is Z5 and Z7 an integral domain?
Yes, it is an integral domain. Yes.
This is an
Both
integral
are
domain.
individual.
Yeah. So both are integral domains. That is right. So, okay, let's add integral domains. Let me give another thing. Let's take Z6. Is this an integral domain?
No,
Not
it
an
is not integral domain because it has a zero divisor.
Yeah. What is a zero divisor?
Uh, say one and sorry, 3 and 2.
Yeah. So the
3
answer
and 2.
is yes. It's not an integral domain because 2 is a zero divisor. 2 into 3 is 0 in this operation. So in general, if you look at Zn, it's an integral domain if and only if n is a prime number. If and only if n is a prime number. Okay. Any questions? We have 5
No.
minutes.
No,
Okay.
ma'am.
Then let's go on to the next question. So, okay, wait. Yeah. So, if R is a ring with unity satisfying xy square equal to x square y square, then for every x and y in R, then is R a commutative ring? Is it an integral domain? Is it a field? So, a field is an integral domain in which every element has an inverse. Every non-zero element has an inverse. So we did something similar to this in the last class, right? If you recall. Anybody wants to give it a try?
Ma'am, it is a commutative ring.
Okay. Why do you say so?
Through multiplying with inverses, I think we can get it as commutative.
But we only know that R is a ring. See, that's the difference. Last time, we were doing it with a group where we could multiply with inverses. Or in other words, this is what I'm saying. We can cancel elements. But in a ring, in a general ring, if you have xy equal to xz, you cannot say that y equal to z, right? Because you don't know if x inverse exists under multiplication. So in an arbitrary ring, xy equal to xz need not imply y equal to z. So we use this in one of our, in the problem that we were solving. So can you think? Anybody wants to at least start it? If not, complete. It's a little bit of a computation.
It is not a group under multiplication.
No. It just says it's a ring with unity. So it need not be a group under multiplication.
Yes, the cancellation holds only when the given pair is a group.
Yeah. So you cannot use cancellation here.
Yeah, yes.
Okay. So this is little bit of a computation and we don't have much time for it. Maybe I'll just write out the computation. It is just, some substitutions and some tricks, and we'll upload it on the drive folder that is shared with you, right? So there's one thing that we wanted to do. So you just look at this last thing because we have not done anything related to fields. So we'll just quickly look at this question because we hardly have 1 minute. So is complex numbers a field under addition and multiplication?
Yes.
Yes.
Yeah. So every complex number, you can actually get an inverse. So let's quickly do it. So a plus ib inverse is 1 by a plus ib, and you can rationalize it. Right? So a square plus b square. So this is a field. Is rational numbers
Ma'am,
under addition? Yeah.
ma'am, there is slight lag in the screen. Now it comes.
Okay. Okay. Maybe I should learn to speak before I write then. Okay. So I was just saying that a complex number, you can find an inverse.
The second one is also
Yeah.
field.
The second one is also a field because if you have a rational number a by b, its inverse would be b by a. And the third one,
The third one is not a field since it has no multiplicative inverse.
this is not a field. And finally, the last one also, you can do something very similar. You can just rationalize it. So you take a plus, you want to find, so see, it is all elements of the form a plus b root 2, where a and b are rational numbers. So 1 by b root 2, you can do this. So I'm multiplying numerator and denominator by 1a minus b root 2. So you'll see that again it comes of the form sum a prime. So it will be a minus b root 2 by a square minus c square. So it is again of the form some rational number plus root 2 times some rational number. So it is a P. So yeah, with that we will stop the class. If you have any questions, we can take it. So this one, there is actually not much new idea here. It's some comparison. I'll probably just put it up.
Ma'am,